Welcome back. We are so incredibly glad you decided to join us today for another deep dive.
Absolutely.
Whether you're prepping for a massive IT strategy meeting, or you're trying to catch up on the latest shifts in enterprise architecture, or maybe you're just one of those insanely curious people who loves knowing how the digital world actually functions behind the scenes, you are in exactly the right place.
We truly have a fascinating journey ahead of us today. It is one of those highly intricate topics that sits completely out of sight. It's entirely invisible to the average person, yet it strictly dictates so much of our daily digital experience.
Okay, let's unpack this. Our mission today is to explore a hidden, highly complex system that essentially acts as the air traffic control for our digital lives. We're talking about enterprise routing. Now, I know what you might be thinking. Enterprise routing. That sounds a little dry. That sounds like something a network administrator mumbles about in a server room. But stick with us, because this unseen machinery is literally the difference between you submitting an urgent help ticket and getting a resolution in 2 minutes versus, languishing in a digital void for 2 agonizing weeks.
Exactly. It's the backbone of the modern customer experience. And the foundational source material we are using to decode this machinery today is a remarkably detailed technical document.
Yeah, it's a dense one.
It really is. It's an internal engineering deep dive from SupportLogic, published recently in March of 2026. And the title really sets the stage perfectly. It's called Why Enterprise Routing is Fundamentally Broken and How IC Fixes It.
And just to set the parameters of what we are looking at today, this document is an extensive technical breakdown, and it looks at how IC operates as a next-generation routing agent.
It is a profound look under the hood. It challenges a lot of the deeply ingrained assumptions that the software industry has just relied on for decades.
Let's set the stage for you, our listener, because, we have all been on the receiving end of this process. You are at work, you have a critical piece of enterprise software crash, or maybe you were locked out of a vital financial account right before a deadline. So you scramble to the company's portal and you submit a customer support ticket.
And then
you wait.
You wait.
And you wait. And you find yourself wondering, in an age of instant global communication, why does it take so long to get a helpful response from a human being who actually knows how to fix your specific problem?
What's fascinating here is that the traditional way companies have tried to solve this using what the industry calls rules-based routing is hitting an absolute breaking point.
Yeah.
It's not that the engineers and the operations managers designing these systems aren't trying. I mean, they are brilliant people working incredibly hard. The issue is that the methodology itself has fundamentally failed to scale. As enterprise companies grow, these human-written static rules transform into an unmaintainable tangle of exceptions.
I want to make this tangible for the listener, because reading a white paper about deterministic logic can get abstract really fast. Let's create a scenario that we can thread through our entire discussion today. Let's invent a support agent. We'll call her Sarah.
Okay, Sarah.
Sarah is a Tier 2 support engineer working for a massive global cloud infrastructure company. She sits at her desk in Chicago, surrounded by multiple monitors, Slack channels pinging constantly, and a queue of incoming customer crises.
That is a perfect framework.
Right.
Because understanding Sarah's daily reality is the absolute key to understanding why traditional routing is fundamentally broken.
Okay, how so?
The source document explains that traditional routing relies entirely on deterministic if-then logic. It utilizes basic parameters, things like skill tags attached to an agent's profile, queue membership, and simple round-robin rotation. It's essentially dealing out tickets like a deck of cards.
And to be fair, the text notes that this actually works perfectly fine in certain scenarios.
Right.
Like if Sarah works for a tiny startup with 3 products, a 5-person support team, and customers who only ever call during normal business hours with highly predictable problems. Then logic is great.
Sure, it works there. But none of those conditions hold true at the global enterprise level. The phrase the document uses to describe the enemy of rules-based systems is combinatorial complexity.
Wait, combinatorial complexity. Let's break that down. Are we just talking about having too many variables to keep track of?
It is more malicious than just having a lot of variables. It means the number of possible combinations of those variables multiplies exponentially. Let's use your agent, Sarah, and look at the specific example the text provides to illustrate this failure.
Yeah, let's do it.
Imagine it is 2:47 a.m. Central Time. A P1, a priority one, the absolute highest level of emergency case arrives in the system. And it's from a massive, highly strategic enterprise account based in Singapore. They are experiencing a catastrophic server failure.
Okay, so a giant flashing red light goes off in the system. The customer needs help right this second.
Exactly. In a traditional rules-based system, a static rules engine springs into action. It looks at this P1 ticket and starts marching down a rigid flowchart, asking very basic binary questions.
Like what?
It asks, is the agent currently assigned to the APAC, the Asia-Pacific queue? Yes or no? It asks, is the agent currently marked as available in the human resources system? Yes or no? It scans the ticket and asks, does the text of this ticket contain the specific keyword critical? Yes or no?
Right, so it's literally just a giant inflexible decision tree. And based on that tree, it finds an agent in Singapore who is marked available, let's call him Dave, and it dumps the massive server failure onto Dave's desk. Problem solved, right?
That is exactly where the illusion of efficiency falls apart. The document points out exactly what those rigid rules absolutely cannot know. That basic flowchart cannot tell you that Dave, despite being in the APAC queue, was just hired 3 weeks ago and has never handled a P1 server failure on his own.
Oh, wow. So Dave is panicking right now.
Exactly. And furthermore, the rule engine cannot know that Sarah, sitting in Chicago at 2:47 a.m., actually spent 2 years as the dedicated account manager for this exact customer in Singapore before moving to Tier 2 support. She knows their custom server architecture intimately.
But the system ignores Sarah because the static rule says Singapore ticket equals APAC queue. It's completely blind to the nuance. I'm going to push back on this a little, though. If the engineers know this is a problem, why don't they just write better rules? Why not write a rule that says, if customer is X and issue is Y, check Sarah's profile first?
It is a valid question, but this is exactly where combinatorial complexity defeats human effort. If you have 10,000 customers, hundreds of product versions, and thousands of agents with constantly shifting schedules, the number of if-then rules you would have to write is in the millions.
Millions of rules.
Millions. Engineers spend months building these elaborate, fragile rule trees, but reality is fluid. The second an agent goes on maternity leave or a customer upgrades their software or a new product is launched, hundreds of those static rules instantly become obsolete or actively harmful.
I see. It's like trying to navigate a massive, sprawling city during peak rush hour. But all you have is a static paper map printed 5 years ago. Sure, the roads are technically drawn on the paper. You can trace a route with your finger. But that paper map doesn't know about the 5-car pileup on the bridge right now.
Exactly.
It doesn't know about the new construction detours or which lane is moving fastest at this exact millisecond. To actually get where you're going efficiently, you need a real-time GPS app that is constantly ingesting live traffic data. The paper map is the rules-based system.
That is a phenomenal analogy. The static map lacks context. And to provide that context, a routing system needs to reason about multiple competing variables simultaneously, weigh them against one another, and recalculate everything dynamically.
Which is incredibly hard to do.
It is. That brings us to how SupportLogic actually approaches this. To abandon the paper map and build the real-time GPS, they had to entirely rethink the architecture. This leads us directly into the machine learning core of the platform, what the engineering document calls the 5-pillar scoring engine.
This is where we get into the really deep mechanics of it. To solve this immense complexity, Intelligent Case Assignment ICA abandons the flowchart entirely. Instead, it computes a dynamic overall score for every single candidate agent on every single eligible case that comes in the door.
Yes, and it does this using a weighted average of 5 independently trained machine learning models. They refer to these models as the 5 pillars. It doesn't just look at one factor, like is Sarah in the right time zone. It evaluates a composite reality of who Sarah is right now, what the customer needs right now, and how those two realities intersect.
Right.
The source actually provides the default mathematical formula used to generate this score.
I know reading math on an audio deep dive can be tough, but I want you to walk us through this formula because understanding what variables they chose to include and what weights they assign to them tells us everything about how this system views human labor.
I completely agree. The default formula provided in the V8.101 plus text is this. Score equals the sum of 0.33 times time overlap plus 0.33 times bandwidth plus 0.17 times customer plus 0.17 times skills. That entire sum is then multiplied by 1 minus the penalty modifier.
Okay, let's freeze right there. Let's look at those weights. What immediately jumps out to me is how heavily time and bandwidth are prioritized. Time overlap and bandwidth each get a massive 33% weight by default. Skills and customer affinity only get 17% each. That seems counterintuitive at first glance. Shouldn't we care most about who has the absolute highest skill?
It seems counterintuitive until you map it onto the reality of a support floor. The system's default weights represent a stark operational truth. Even if you have the world's absolute greatest expert on a highly specific database problem, meaning they score perfectly on the skills pillar if their bandwidth pillar is at 0 because they already have 20 open cases, or if their time overlap is terrible because they are logging off for the weekend in 5 minutes, they are completely useless to the customer who is panicking right now.
Okay. So applying this back to Sarah in Chicago and our P1 ticket from Singapore, the rule-based system gave the ticket to Dave because of a rigid geographic rule. Let's look at how the ML formula handles it.
Let's do it.
The system calculates a score for Dave. His time overlap is great, he's in Singapore, but his skills pillar is very low for this severe issue. And maybe his bandwidth is strained because he's slow at resolving things.
Exactly. And simultaneously, it calculates a score for Sarah. Her skills pillar is incredibly high because of her history with the account. Her customer pillar is high because she knows them. And let's say she just logged on for a night shift, so her time overlap and bandwidth are excellent. The math definitively proves Sarah is the better choice, regardless of what queue she technically sits in.
And the result is a clean score ranging from 0.0 to 1.0, which the user interface then renders for managers as a percentage from 0% to 100%. Sarah might score a 94%, while Dave scores a 41%.
What this represents is a massive foundational architectural shift in software engineering. It transforms enterprise routing from a classification problem into an optimization problem.
I really want to pause on that. Classification versus optimization. I know what classifying a ticket means. I imagine someone's sorting mail into little cubby holes. But what does optimizing it actually look like in this specific context?
The mail sorting analogy is perfect for classification. The rules engine looks at a letter and says, this has a Chicago zip code, put it in the Chicago bucket. It stops thinking the moment the letter hits the bucket.
Right, it's done its job.
Done. An optimization problem, which is the realm of machine learning, asks a vastly more complex question. It asks, given everything we know in this exact millisecond about the severity of the case, the history of the customer, the latent skills of every single available agent globally, and the current mental workload of those agents, what is the absolute best possible pairing we can make right now to resolve this fastest?
It's the difference between finding a solution that is merely good enough versus calculating the mathematically optimal path forward.
Precisely. And what this optimization approach enables is a crucial concept that the document highlights, known as graceful degradation.
I love that phrase. Graceful degradation. It sounds like a fading Victorian mansion, but in software, it's a lifeline. Explain how it works for Sarah.
In a rigid rule system, if the rule strictly mandates route all Singapore P1 tickets to Agent Dave, but Dave's computer just crashed and he is abruptly offline, the rule violently breaks.
It just fails.
It fails. The system doesn't know what to do, the P1 case sits unsigned, or it falls into a massive hidden catch-all bucket where it languishes unnoticed while the customer servers burn.
But with IC's continuous scoring engine.
With continuous scoring, there is no breaking point. If Sarah is the mathematically optimal choice with a 94% score, but Sarah steps away for a 15-minute coffee break, the system doesn't panic. It gracefully degrades. It instantly looks at the real-time matrix and falls to the next best agent, perhaps someone with an 88% score.
And if they are busy.
If they are suddenly busy, it gracefully degrades to the 81% score. The system never breaks. It just continuously, fluidly finds the next best optimal path available in that specific millisecond.
Now, I want to go back to the formula for a second. We talked about those default weights, the 33% and the 17%, but the document is very clear that these aren't locked in stone by the developers.
That is a critical feature. Customers can customize these weights to reflect their unique business realities, and importantly, it requires zero actual code changes on the customer's end. They simply submit a model update request via Jira, which is just the standard internal ticketing system IT teams use to track work, and the SupportLogic machine learning team adjusts the back-end weights.
The text gives a fantastic example of why a company would actively want to mess with those defaults.
Yeah.
Let's imagine Sarah doesn't work in general cloud infrastructure anymore. Let's imagine she works for a highly regulated financial institution, maybe handling compliance audits.
In that environment, the priorities shift dramatically. For a compliance team, ensuring an evenly distributed, fast workload is vastly less important than making sure the absolute most qualified, legally certified expert handles a highly sensitive regulatory ticket.
Right. Speed isn't the priority. Accuracy is.
Exactly. If a bank auditor submits a ticket, you do not care about graceful degradation to an 81% match. You want the 99% match, even if it takes longer.
So the manager of that financial team would submit a JIRA request to radically alter the formula. They might say, increase the skills weight from its default 0.17 all the way up to 0.40 and drop the bandwidth weight down to 0.25. They are intentionally telling the machine learning model to prioritize deep, specific expertise over an evenly balanced queue.
It allows the operational business logic to dictate the machine learning priorities rather than forcing the business to conform to the algorithm's defaults. But all of this mathematical optimization hinges on one massive assumption. It assumes the system actually accurately understands what a skill is, which segues into a much deeper problem. How does a machine know what Sarah's actually good at?
This brings us to a fascinating part of the document, skills intelligence beyond keyword matching. And I had to say, this is where traditional CRM software usually falls completely flat.
It does. In legacy systems, as we mentioned earlier, a skill is nothing more than a boolean flag. It is a simple binary checkbox manually ticked on an employee's profile by a manager. Does Sarah know SQL database querying? Check the box. Does she know Linux server configuration? Check the box.
The problem with a Boolean checkbox is that it has no nuance. It treats Sarah's passing familiarity with Linux exactly the same as Dave's 10 years of deep kernel-level Linux engineering. A checkbox is a terrible representation of human knowledge. ICA throws the checkbox out. It treats skills not as static labels, but as learned, continuously updated signals derived from the actual living history of resolved cases.
To achieve this dynamic understanding, the document details how ICA utilizes three specific, distinct machine learning models working in constant tandem. These are the case skills model, the agent skills model, and the skill matching model.
Let's take these one by one, because the case skills model uses technology that has been making massive headlines recently. It utilizes large language models, or LLMs, for actual logical inference, not just blindly scanning a ticket for keywords.
This is a profound leap forward in natural language processing within support routing.
I'm going to set up an example, because the difference between keyword scanning and logical inference is massive. Let's say a frustrated customer types into the support portal, "I've been trying to get in for an hour." The screen just freezes every time I hit enter on the login page.
In a legacy system, the rules engine searches the text string for the exact keyword, password reset, or authentication. Because the customer used colloquial language, try and get in, screen freezes, the keyword scan fails entirely. It categorizes the ticket as a generic UI glitch and routes it to the wrong team.
But the SupportLogic case skills model uses an LLM. It has been trained on millions of interactions. It reads that text and understands the semantic intent. It infers that trying to get in and log in page freeze intrinsically require the authentication skill, even though the customer never explicitly typed those exact words. It understands human frustration and intent, not just vocabulary.
That is the case skills model analyzing the incoming demand. It asks, what does this problem require? Then you have the second model, the agent skills model. This analyzes the supply side, the humans. This model automatically scans every agent's entire historical case resolution log on a monthly basis. And crucially, to make sense of this massive amount of data, it employs a statistical method called TFIDF weighting.
Okay, hold on. TFIDF weighting.
Yeah.
If I'm an IT director prepping for a meeting, that sounds like the exact kind of heavy data science jargon I need translated. What does that actually mean for Sarah?
It is a vital concept to grasp. TFIDF stands for Term Frequency Inverse Document Frequency. The acronym isn't important to memorize, but the mathematical concept is brilliant. It is an algorithmic way of preventing highly common everyday tasks from falsely dominating an agent's skill profile.
Let's apply this to Sarah's monthly review. What does TFIDF actually look like in practice?
Imagine Sarah is incredibly fast and helpful. Over the course of her month in Chicago, she resolves 100 simple, routine password reset tickets simply because those tickets make up a massive volume of the daily queue. She knocks them out quickly between her harder cases.
Without TFIDF, a basic statistical model would look at her sheer volume of resolved tickets, see 100 password resets, and conclude, wow, Sarah spends 60% of her time doing password resets. She must be the ultimate specialized expert in password resets. Let's route every single password issue to Sarah forever.
Exactly. She gets severely punished with mind-numbing repetitive work precisely because she was efficient at it.
That is the fastest way to make a brilliant engineer quit.
It is a massive cause of burnout. But TFIDF introduces context. It essentially looks at the data and says, yes, Sarah did 100 password resets. However, the inverse document frequency part of the math shows that password resets are incredibly common across the entire global company. Everyone does them. Therefore, doing a lot of them doesn't indicate specialized expertise. It just indicates high operational volume.
Oh, that's incredibly smart. So the math inherently deprioritizes common tasks.
Yes. It prevents the mundane, high-volume noise from drowning out the rare, complex skills that Sarah actually possesses. If Sarah solves just 2 catastrophic BGP routing protocol failures in a month, TFIDF flags that as incredibly rare and highly complex. It elevates it to the top of her skill profile even though the volume was low.
So we had the case skills model figuring out what the ticket needs, and the agent skills model figuring out what Sarah is truly uniquely good at. The third piece, the skill matching model, is the bridge. It takes those 2 realities and collides them to produce that hard percentage score we talked about earlier. And the document note's a great UI feature here. For transparency, the system surfaces the top 5 matching skills directly in the user interface.
Transparency in machine learning is not just a nice to have, it is an absolute operational necessity. If Sarah or Sarah's manager cannot look at a screen and understand exactly why the algorithm paired her with a specific Singapore server ticket, they will lose trust in the system entirely. Surfacing the why validates the math.
Now, looking ahead, the document outlines a fascinating future roadmap feature regarding these skills. And it attempts to tackle a problem every support worker knows intimately.
Yes. The roadmap indicates that soon, specific skills will actually carry dynamically higher weights in the overall formula based purely on their inherent technical complexity.
Let's talk about the implications of this because it feels profound for workload management. The text contrasts a kernel panic case with a standard password reset. A kernel panic, which is a severe, deep-level operating system crash, requires vastly more cognitive effort, research time, and pure mental stress to resolve than clicking a button to reset a password.
In legacy systems, a ticket is a ticket. The rules engine counts a kernel panic as one case and a password reset as one case.
So Sarah could be assigned 5 kernel panics in a row, and the system thinks she has the exact same workload as Dave, who just got assigned 5 password resets.
Exactly, which is absurd. The upcoming feature will allow the ML to recognize that asymmetry. It will mathematically understand that resolving one data corruption ticket drains the same mental battery as resolving 50 password resets. Therefore, the system will actively limit how many of these highly complex, brain-draining cases a single agent like Sarah receives in a single shift.
It's essentially building psychological burnout prevention directly into the routing algorithm. It's trying to mathematically model human cognitive load.
It is a massive evolutionary step beyond simple time tracking. But here is the catch, and this is a crucial transition. None of this brilliant ML scoring, none of the LLM inference or TFIDF weighting matters at all if the system doesn't have a structural foundation to operate within. It needs a physical architecture to place the tickets into.
Which brings us to a major architectural discussion in the document. Queue architecture CRM versus virtual queues. The text explicitly states that ICA is designed to sit exactly at the layer where rigid business logic meets fluid machine learning.
To organize the immense flow of work, ICA utilizes 2 entirely different types of queues, CRM queues and virtual queues. Let's examine CRM queues first, as they are the baseline.
A CRM queue is exactly what it sounds like. It's a queue imported directly from whatever underlying system of record the company is already paying for, whether that's Salesforce, ServiceNow, Zendesk, or Microsoft Dynamics.
But the vital architectural detail to understand here is that ICA only imports the names of these queues. It strictly refuses to import the internal routing logic or the messy legacy rules from Salesforce. It just looks at Salesforce and says, okay, you have a bucket labeled Tier 1 support.
The document advises that these basic CRM queues are best used for simply mirroring existing rudimentary structures, usually when a company is first deploying SupportLogic and wants to maintain some familiarity.
They are the legacy foundation. They are safe. But virtual queues, this is where the architecture becomes truly dynamic and, frankly, revolutionary for system administrators. Virtual queues are native entirely to SupportLogic. They do not exist in the underlying CRM at all, and they are highly composable, utilizing strict AND or boolean logic.
Here is where it gets really interesting for anyone who has ever had to beg an IT admin to change a routing rule. Because virtual queues exist above the CRM, you can combine practically any data points, custom fields, account sizes, product groups to handle complex, cross-cutting business emergencies without ever having to call your Salesforce administrator to reconfigure the entire back-end database.
The agility this provides is immense. Let's use the exact example provided in the source text to illustrate the power of this composability. Let's imagine our company just discovered a massive vulnerability in our security platform.
The text provides this logic string to create a virtual queue on the fly. Priority equals critical, or priority equals urgent, ND product group equals security platform.
Now consider the legacy approach. In a traditional CRM, building a specific temporary routing workflow for that exact sudden combination of variables might require submitting a ticket to the CRM administration team, waiting for them to write custom code, testing it, and deploying it days later. By then, the security crisis has overwhelmed the company.
But with a SupportLogic virtual queue, Sarah's manager just types that logic string into a clean interface. And instantly, within seconds, they've created a specialized virtual environment. It allows a tiny, highly specialized team of security experts to see only the massive, urgent security issues isolated from the noise. Meanwhile, the general queue continues handling the rest of the daily traffic completely undisturbed. And they achieve this operational miracle without touching a single setting in their core CRM.
It completely decouples routing logic from CRM administration, which eliminates a massive operational bottleneck. But creating these brilliant queues is only half the battle. Once you have 5 different queues, you have to definitively tell the machine learning model the order in which they must be processed.
And that leads us to a massive, highly anticipated feature detailed in the document, rolling out in Q2 of 2025, cross-queue prioritization.
This feature allows system administrators to force the system to completely drain high-priority queues before the ML is even allowed to look at lower-priority ones.
The document references a very specific real-world use case to explain why this was developed from a company called Gainsight. I want to spend some time on this because the Gainsight use case perfectly illustrates how algorithmic efficiency can accidentally destroy a support team if business priorities aren't enforced.
It is a textbook example of unintended consequences. Gainsight's support team was facing a very real, very frustrating systemic problem. Their agents were getting absolutely bombarded with a massive, relentless volume of low-priority, easy-to-solve tickets.
Right, and because the agents were diligently working through the sheer volume of easy tickets, they were constantly hitting their maximum daily capacity limits. The algorithm was filling their plates with appetizers.
Exactly. And because the agent's plates were full of low-priority noise, when a massive, high-priority, critical ticket, the main course, finally came into the system, the routing algorithm looked around and saw that every single agent was mathematically at capacity. The low-priority noise was literally blocking the critical signals from being assigned.
The algorithm was technically working flawlessly, according to its capacity rules, but strategically, it was failing the business. So Gainsight needed a way to tell the algorithm to stop being so egalitarian.
By implementing cross-queue prioritization, they solved the bottleneck. The system architecture now mandates a strict hierarchy. It says to the ML, stop. I do not care if there are 500 low-priority tickets waiting. We have a queue designated for critical server failures. We are going to process, score, and assign every single ticket in that critical queue first. Only when that high-priority queue hits absolute 0 are you allowed to even calculate scores for the low-priority queue.
It essentially forces human business priorities onto the raw efficiency of the machine learning engine.
It is the business logic constraining the math. And that concept of constraints how many tickets an agent like Sarah can physically handle before the system forcefully stops assigning them work is a perfect transition into the next critical component of the architecture. Let's examine the availability layer.
This is a vital distinction the document makes. The difference between hard limits versus soft scoring.
The architecture of ICA structurally separates its ML soft scoring, that dynamic 0 to 100% we spent so much time on earlier, from hard availability limits. And crucially, they operate sequentially.
What does that mean in plain English for Sarah sitting in Chicago? It means that even if the machine learning engine looks at a highly complex Singapore ticket and calculates, wow, Sarah's TFIDF history is incredible, she is a perfect 100% mathematical match for this case. If Sarah has hit a hard capacity limit, she's entirely blocked. The perfect ML score doesn't matter. The math is overridden. The hard limit always wins.
The ML soft scoring is designed to answer an optimization question. Out of the pool of eligible people, who is the absolute best person for this job? The hard availability limit, however, sits in front of the ML and answers a much more foundational binary question. Is this specific human being even legally, physically, or operationally allowed to be handed a new piece of work right now?
Let's walk through the 4 distinct sources of availability that the ICA system checks, because it checks them in a strict priority order. Number one, the most basic. Shift assignment and working hours. This is fundamental scheduling. If Sarah is not scheduled for a shift or she has an an O marker on her calendar because she's at the dentist, that time is subtracted. She is completely unavailable to the ML symbol.
Number two is CRM omnichannel presence. For enterprise customers deeply embedded in Salesforce, for example, the agent's presence status is read in real time. If Sarah steps away from her desk to grab lunch and clicks busy in the Salesforce widget, SupportLogic instantly reads that state change via API. This means she doesn't have to update her status in two separate systems, which agents notoriously hate doing.
Number three is essentially the same concept, but for non-Salesforce systems. It's a custom CRM field. This is the equivalent feature for platforms like ServiceNow or Zendesk, where administrators map a specific custom field to signal real-time availability back to SupportLogic.
But number four is where the system shows its resilience. It is the fallback mechanism, ML predicted active hours.
I am going to push back on this one, because when I first read it, it sounded a little like Big Brother. Predicted active hours. Is the system literally spying on Sarah to guess when she's sitting at her desk?
It's a common concern, but it's not surveillance. It's statistical inference. If a company has poor IT hygiene, if they haven't configured proper shifts in step 1, and they aren't paying for real-time CRM presence in step 2 or 3, the ICA system doesn't just throw up its hands and crash. It needs to keep routing tickets.
So how does it guess?
It analyzes Sarah's historical activity patterns. It looks at the metadata. When does she typically open cases? When does she typically send her first email of the day? When does the volume of her keystrokes in the CRM drop to 0? Based on that historical data, the ML builds a predictive model of her likely working hours. It is vastly less precise than a strict schedule, but it acts as a safety net, keeping the routing engine functioning even when the administrative configuration is incredibly poor.
Okay, that makes more sense. It's reading system logs, not turning on her webcam.
Yeah.
Now, beyond those binary states of working or not working, we must look at the actual hard limits that govern how much work she can take while she is at her desk. There are two primary limits discussed in the document. First is the active backlog limit.
This is a strict, unyielding cap on the total number of open, unresolved cases an agent can hold in their personal queue at any one time.
So if Sarah's manager sets her active backlog limit to 15, and she currently has 15 open cases she is researching, hitting that exact number triggers a state change. The system forces her bandwidth calculation to 100% full. It is a hard stop. The ML engine is blocked from assigning her case number 16, no matter how perfectly her skills match the ticket.
The second limit operates slightly differently. It is the hourly assignment limit. This is a rolling window cap.
I found this fascinating. Why do we need an hourly limit if we already have a total backlog limit protecting her?
Because you have to protect the agent from what engineers call burst overload. Let's look at Sarah's schedule. Imagine she logs in at 8:00 a.m. on a Monday morning after a long weekend. Over the weekend, 50 new cases piled up in the system queue. If Sarah's only protection was a backlog limit of 15, the instant she clicked, available at 8:01 a.m., the incredibly fast ML engine might instantly blast 15 highly complex cases onto her desk all at once.
Getting hit with 15 emergencies in your first minute of work is a phenomenal way to induce an immediate panic attack.
Precisely. The hourly assignment limit acts as a throttle. It says even if Sarah's backlog is completely empty and she could technically hold 15 cases, you are only allowed to assign her a maximum of, say, 3 new cases per hour. It paces the work, allowing her to ingest the complex information smoothly over the course of her shift.
I love that. It's like a metronome for enterprise stress. It regulates the heartbeat of the support floor. But if we connect this to the bigger picture of system architecture, what happens when all these well-intentioned rules inevitably conflict with each other? The document explicitly outlines an operational law called the lowest limit wins rule.
It is an ironclad mathematical principle of the system. Let's say an administrator sets Sarah's daily limit to 10 cases, but her manager sets an hourly limit of 2 cases. If those limits clash at a specific moment in time, say, she has only had 4 cases today, but 2 in the last hour, the tighter, more restrictive boundary always applies. She gets nothing until the hour rolls over.
And there is a vital hierarchy to these overrides that the text makes very clear. While certain high-priority routing rules, like a massive P1 server outage, can be programmed to override general capacity limits in a break-glass emergency, they can never override an out-of-office status or an out-of-hour schedule.
The system respects human boundaries. If Sarah is scheduled to be on vacation in Mexico, the system will not route a P1 ticket to her queue, no matter how flawlessly her skills match, and no matter how much the company's servers are burning down. Her OO status is an impenetrable shield against the routing engine.
Which is a massive relief for anyone who has ever been sitting on a beach and gotten a terrifying Slack alert from their boss. But all of this intricate overlapping logic, the ML scoring, the virtual queues, the hard limits, raises a very serious operational question for an IT director. What happens when this massive, invisible, algorithmic brain makes a mistake? What happens when the underlying data pipelines fail?
Which brings us to a critical failsafe detailed in the document. Section 6. Observability when the system fails. The engineering team highlights a major update introduced quite recently in February 2026, the customer-facing alerting framework.
Let's talk about the era before this framework, because the document paints a grim picture. Prior to this alerting system, if a company had a subtle misconfiguration in their queues, they risked a terrifying scenario called a silent failure.
A silent failure is the nightmare scenario for an operations director. The ML engine might still be running perfectly, calculating scores, but due to a broken queue link, the cases aren't actually reaching the agents. They are just piling up in a hidden, disconnected virtual bucket, entirely unnoticed by the support team.
And the only way the company discovers the failure is 3 days later, when a massive enterprise customer calls the CEO directly, screaming that their critical tickets are being ignored.
Exactly. The system lacked observability. So SupportLogic built this alerting framework specifically to drag those silent failures into the light, and it operates on a dual track. When it detects a failure, it sends alerts both to the customer's designated IT email list and to an internal SupportLogic DevOps mailing list simultaneously.
But what I find really smart from an engineering perspective is how they structured the alert thresholds to avoid the classic boy who cried wolf scenario.
You are referring to alert fatigue, a massive problem in IT. If a monitoring system pages a DevOps engineer on their phone every single time a single minor API timeout occurs, the engineer eventually becomes desensitized and starts ignoring the pager entirely. To prevent this, the ICA framework uses strict aggregation thresholds across 3 distinct tiers of severity: warning, urgent, and critical.
Let's banter through these tiers, because the specific thresholds show exactly how the system logically evaluates risk. The lowest tier is a warning.
A warning is typically triggered by operational realities on the support floor, not necessarily code breaking. For instance, imagine a scenario where the ML correctly assigns a ticket to 5 different eligible agents in sequence, but all 5 manually click decline because they are too stressed. The system flags that. Or if there are simply 0 agents marked available globally in a specific queue, or, paradoxically, if the system finds 100 matching agents for a niche ticket, indicating that an administrator made a queues filters way too broad.
But the crucial part of a warning is the threshold. The system won't fire off an email the very first time an agent declines a ticket. The threshold is defined as 10 occurrences within a rolling 1-hour window. The system needs to see a persistent, undeniable pattern of operational failure before it bothers tapping a manager on the shoulder.
Moving up the severity scale, we reach urgent alerts. These are no longer just operational hiccups, these are actual technical infrastructure failures.
An urgent alert means the vital CRM sync has failed. That means SupportLogic has fundamentally lost the ability to talk to Salesforce or Zendesk. Or it means one of the 5 ML pillars itself has crashed in the cloud, completely stopping auto-assignment.
Because these are severe system failures that halt business, the threshold is significantly tighter. 5 occurrences within a tight 30-minute window. This structure gives the system a brief, momentary window to attempt to self-heal or retry the API connection, but it escalates quickly if the failure persists.
And finally, we have the critical tier. If we were in a submarine, this is when the red lights are flashing and the klaxons are blaring. This is the DEFCON 1 scenario.
A critical alert is triggered by catastrophic, unhandled software exceptions deep within the code that bring the entire auto-assignment engine to a complete hard halt.
The threshold here is incredibly tight, just 3 occurrences in 15 minutes. And the action required isn't just an email to a manager, it is an immediate, high-priority escalation directly to the DevOps or Network Operations Center teams. It's essentially the system screaming, "I am deeply broken at a structural level, I cannot self-heal, wake somebody up right now before we lose data."
The intentional design here is elegant. As the text notes, a single momentary ML glitch doesn't trigger a company-wide urgent alert. It requires that persistent, aggregated pattern. It balances the need for total operational visibility with the vital need to maintain the sanity and sleep schedules of the IT staff.
Okay, so we have covered a massive amount of ground. We've talked about the mathematics of the ML formula, the LLM inference for skills, the composability of virtual queues, the strict hierarchy of limits, and the alerting alarms. But how does a company actually build this incredibly complex machine without accidentally breaking their existing support operations? That brings us to Section 7, Implementation of the Golden Sequence.
And we need to spend some real time here because the engineering document is incredibly emphatically firm on this point. ICA's transformative power depends entirely on correct sequential configuration. The document outlines a strict 8-step sequence. And it explicitly warns in bold text that skipping steps or attempting to do them out of order because you were in a rush is the single most common reason for poor ML recommendation quality. If you build it wrong, the ML learns the wrong things.
I am going to list these 8 steps sequentially, and I want you to explain to our listener exactly why the order is so vital. Imagine we are sitting in a conference room with Sarah's IT director planning the rollout. Step 1, validate or build the ontology. What does building an ontology actually look like in practice?
Yeah.
Are they just making giant Excel spreadsheets of keywords?
It's much deeper than a spreadsheet. The ontology is the master foundational dictionary of every technical concept, product, and skill relevant to the specific company. It defines the relationships between concepts. If you skip this step because it feels tedious, the ML has no vocabulary. It is effectively blind. As the text explicitly warns, if you do not build the ontology first, every single agent, including brilliant engineers like Sarah, will score a 0% on the skills pillar, rendering the entire massive ML engine completely useless. It absolutely must be step 1.
That makes total sense. You can't ask a machine to read if you haven't taught it the alphabet. Okay, step 2, create virtual teams.
Notice that you do this before you touch any queues or schedules. You group your agents into logical functional teams first. Why? Because teams act as reusable architectural blocks. If you build the teams first, any adjustments you make to a team's membership later, like Sarah moving from the US team to the global escalation team, will automatically propagate perfectly throughout the entire labyrinth of downstream queues and rules. It creates a single source of truth for human grouping.
Perfect. Step 3, configure shifts.
Now that you have your functional teams built, you define exactly when they are allowed to work. You set their strict working hours and their specific assignment hours in the system. As we discussed in the availability section, if you skip this mundane scheduling step, the system is forced to rely on that less precise ML prediction fallback model to guess when people are working. You always want hard data over predictive guesses when it comes to human availability.
Okay, we have our vocabulary, our teams, and our schedules. Step 4, create queues and link agents.
Here is where the architecture takes shape. You actually build the CRM integration and construct those highly composable virtual queues we marveled at earlier, and you attach the teams you built in step 2 to those queues. The document strongly advises setting up your high-level priority buckets right from the very start during this step.
Why from the start?
Because attempting to retrofit complex priority logic into a massive live flowing system later is operationally dangerous. It is much easier to build the plumbing correctly before you turn the water on.
Makes sense.
Right.
Step 5, configure queue rules.
This step is the fine-tuning of the engine. For each individual queue you just built, you define the operational parameters. You set the round-robin rotation rules, you define the maximum daily cases allowed to flow into that specific queue, and you define the exact hours when the queue is actually active and accepting tickets.
Step 6, set cross-queue prioritization.
The text notes this is a step administrators often mistakenly skip because they assume the ML will just figure it out. It won't. This is where you explicitly tell the system you must always completely drain the critical security queue before you are allowed to look at the general help queue. If you skip this step, high-priority crises and low-priority password resets end up fighting in the ML engine for the exact same pool of agents, leading to the gain-site catastrophe we discussed.
Step 7, configure agent capacity limits.
This is a crucial step for human resource management, especially regarding onboarding. This is where you set those active backlog and hourly limits we discussed. Let's look at Sarah again. When Sarah was a brand new hire on her second day, her manager used this step to protect her. They set her hourly limit to 1. They severely restricted her flow so she wouldn't be overwhelmed by complex enterprise tickets while she learned the ropes. Now that she's a veteran, her limit is much higher. This step allows the system to scale with the human's growing capability.
And finally, the moment of truth. Step 8, enable auto-assignment and monitor.
Notice it says monitor. You do not just flip a giant switch and go to lunch. The golden sequence advises starting incredibly small. Enable auto assignment on one single, non-critical, low-volume queue. Then, the IT director must sit and watch the recently assigned tab in the dashboard like a hawk for 24 to 48 hours to ensure the theoretical logic they built actually holds up when exposed to the chaos of real customer data.
And there's a really cool technical detail from the document regarding this monitoring phase that I want to highlight. The text notes that the ICA data ingestion service is actually 50% faster than the standard Fivetran data pipeline path.
Let's briefly explain that for the listener. Fivetran is essentially an industry-standard piece of data plumbing. It moves massive amounts of data from a CRM like Salesforce into a data warehouse. It's reliable, but it has a slight delay.
Right. So what SupportLogic is saying is that they built their own custom ingestion service that bypasses that standard delay. It is 50% faster. That means when that IT director is sitting there watching the recently assigned tab during step 8, they aren't looking at data from 10 minutes ago. They're seeing near instantaneous real-time feedback on their configuration choices.
Which is absolutely essential. When you are trusting an invisible algorithm to run the core of your support operations, you need to see exactly what it is doing the exact second it does it.
Which brings us to our outro and the ultimate philosophical goal of all of this technology. We've just spent the last hour diving incredibly deep into the weeds of combinatorial complexity, LLM intent inference, TFIDF statistical weighting, virtual queue composability, and fail-safe alerting frameworks. We followed Sarah's journey from being overwhelmed by bad rules to being perfectly optimized by an algorithm. So, taking a massive step back, what does this all actually mean for the future of enterprise software?
To answer that, I think we have to look closely at the closing thoughts provided in the source material. There is a direct quote from SupportLogic Engineering that perfectly encapsulates the entire philosophy driving this immense technological effort. They write, the goal isn't to automate routing. The goal is to make routing so reliably good that your support managers can spend their time on the work that actually requires human judgment.
I have to admit, that gave me a bit of pause when I read it. The entire massive multi-million-dollar engineering effort isn't about replacing the human beings. It's about removing the terrorizing friction of the system so the human beings can actually do the high-level cognitive work they were hired to do.
It is about making the system completely functionally invisible. The highest compliment an IT director can give a system like ICA is that nobody on the support floor ever actively thinks about it. For agents like Sarah, the chaos of cherry-picking tickets and fighting with rigid CRM rules simply vanishes. Cases just magically arrive on her screen, precisely matched to her latent skills, at the exact right time in her shift, with the exact right context needed to solve them.
And that brings me to a final, slightly provocative thought for you, our listener, to take away from this deep dive. We've just spent this hour analyzing how incredibly advanced machine learning can seamlessly map an individual's latent, unstated skills using LLMs. It can mathematically calculate their real-time mental bandwidth and fatigue limits, and it can instantly align all of that human capability with complex, constantly shifting global business priorities to perfectly optimize a massive workforce. If this logic, this intelligent case assignment works so flawlessly for customer support agents, how long do you think it will be until this exact same optimization framework escapes the IT department and is applied to your entire career?
This raises a profoundly important and perhaps unsettling question for the overall future of work. Imagine a corporate future, maybe not that far off, where your daily projects, your quarterly goals, the cross-functional teams you're placed on, and even your opportunities for promotion are no longer assigned by a human manager relying on their flawed, biased, rules-based intuition. Imagine instead that a silent ML model is continuously operating in the background of your entire company. It is constantly calculating your personal TFIDF skill score based on the complexity of the emails you write, the spreadsheets you build, and the code you commit. It is constantly monitoring your hourly burnout limit. Are we rapidly moving toward a global economy where all human routing in every single profession becomes entirely invisible and mathematically optimized?
It is a wild, slightly intimidating, but undeniably fascinating future to think about. Will your next major career opportunity be handed to you by a mentor? or optimized for you by an algorithm that understands your skills better than you do. Thank you so much for joining us on this incredibly extensive deep dive today. We really hope this exploration of enterprise routing has given you some powerful aha moments, demystified the massive systems running behind the scenes, and encourages you to think about how moving from simple classification to algorithmic optimization might just change your own workflow and maybe your own future. Until next time, keep learning, keep questioning, and always look closely at how the systems around you actually work.